Okay, what if I told you that the secret to surviving a 3 year mission to Mars has less to do with rockets and engineering and everything to do with a branch of abstract math? We're going to explore how its elegant, kind of predictable rules could help us solve one of the most unpredictable challenges we've ever faced. Right? It's a fair question. I mean, when we think about the math for space travel, we're thinking physics, trajectories, orbital mechanics, that kind of stuff. But the single greatest variable, the one thing that could make or break the entire mission, well, it has nothing to do with the hardware.
You see, the most complex system on a 3 year trip to the Red Planet isn't going to be the life support or the navigation computer. Nope, it's going to be the small handful of humans locked inside that spacecraft. The success of the entire mission, it all comes down to them.
So, to really understand the solution here, we first have to wrap our heads around the scale of the problem. Sending people that deep into space means putting them in an environment that, let's be honest, humans were just never built to handle for that long. Researchers have a name for these places: isolated, confined, or extreme environments. ICE for short. You find them here on Earth. Think Antarctic research bases or deep sea submarines. But a spaceship hurtling towards Mars, that is the most intense, the most unforgiving ice environment you can possibly imagine. And when you look at studies from these places, man, it reveals a brutal psychological gauntlet. We're talking mood disorders, really intense interpersonal stress, and just constant social friction. Now, add on top of that this deep sense of loneliness and the physical strain of microgravity totally messing with your sleep, and you've got a recipe for disaster millions of miles from home. So, how in the world do you build a team that can actually withstand all of that? Well, the answer, and this is pretty wild, might be hiding in an unexpected toolkit, a branch of pure math called linear algebra. It gives us this kind of perfect, abstract blueprint for success. Which brings us to this idea of a vector space. Now, let's just forget all the complex math for a second and just think of this as a perfectly designed system. It's like a whole universe of objects, we call them vectors, that all interact with each other in completely predictable ways, all based on a very specific set of rules. And these are the rules, the 8 axioms. Don't worry, there's not going to be a test. The only thing that matters here is that these rules make sure the whole system is stable, consistent, and totally reliable. Everything has its place, and every single interaction follows a pattern you can count on. It's basically a blueprint for a perfect system. So, okay, if a vector space is our perfect system, how do we actually build one? Well, in math, you do it with something called a basis. And this, it turns out, is a really brilliant way to think about building the perfect astronaut crew. A basis is the absolute core set of building blocks for that vector space. Think of it like the most efficient starter kit you could ever get. It has just enough fundamental pieces to create everything else in its universe with absolutely zero waste. No fluff, no redundancy. And this is where it all clicks. In math, linearly independent means that every single vector in that basis is unique and totally essential. For a crew, that means every astronaut has a unique, non-redundant skill set. You got the geologist, the doctor, the engineer. Then there's spanning the space. In math, it means the basis can be combined to create any other vector. For the crew, it means their combined skills can handle any challenge the mission could possibly throw at them. So the basis isn't just any team, it's the perfect team, the smallest, most efficient, most versatile group you could possibly put together. I mean, it's a beautiful model for a perfect team, right? But what happens when you take this pristine mathematical system and you subject it to the intense, messy pressures of a real Mars mission? Well, the reality is, this system doesn't exist in a bubble. It's constantly getting battered by stressors. You've got all these different pressures: social, psychological, physical, and they don't just act alone. As you can see here, they combine, they compound, and they just start chipping away at the stability of the team. Get this, a study that simulated a long mission found something really fascinating. While most types of stress actually went down as the crew got used to things, social stress did the exact opposite. It actually spiked right in the middle of the mission. Just being stuck with the same small group of people starts to grind you down, and it weakens the very bonds that make the team work. And then you've got sleep, or, the lack of it. On the International Space Station, astronauts are scheduled for 8.5 hours of sleep a night, but on average, they only get about 6.5. So why is that? Well, microgravity just wreaks havoc on the body's sleep cycles. And this chronic sleep deprivation doesn't just make people tired, it actually degrades their ability to deal with other people. you get more irritable, your social adaptability plummets. In our model, it's like this invisible force that's actively trying to break down the team's basis, to tear apart that cohesion.
So the challenge is crystal clear. It's not enough to just assemble a perfect basis for a team. You have to actively protect it from all the forces that are trying to tear it apart. The math gives us the blueprint, and the psychology tells us how to build it to last. So, the takeaway is really a three-part strategy. First, you select for linear independence, which means choosing people not just for their unique technical skills, but for their proven psychological stability. Second, you train for span. You use tools like computer-based simulations for conflict resolution and stress management to make sure the crew is ready for anything. And third, you protect the basis itself. You actively fight those stressors, you give them sleep aids, you give the crew the tools they need to manage that unavoidable social friction. You see, the lesson from linear algebra is actually pretty profound. The strongest, most resilient systems, whether they're mathematical or human, are always built from a foundation of essential, unique, and comprehensive parts. No redundancy and no gaps. And look, this isn't just about astronauts. This whole idea of building a basis is a really powerful way to think about any high-stakes team, whether that's a startup, a surgical team, or a research group on the ground. It's all about building efficiency and resilience right from the very beginning. So think about the teams that you're a part of. Who are the essential, the non-redundant members? And do you, all together, have what it takes to span the space of whatever challenges you're facing? What is the basis for your team?